In this screencast, we're going to tackle spring force and spring energy, two pretty big topics on the AP test. It turns out there's a lot of AP Physics 1 questions that involve spring. So let's make sure we get our heads well wrapped around these things. Okay, so spring force is kind of interesting in this sense. So let's just say I have a spring that is in a completely relaxed state. I just pulled out the drawer, I haven't done anything to it. We say that that spring is in its equilibrium position. That means it doesn't, this is where it's going to be if you don't put any force on it. Let's just say this side here is attached to a wall, and this side here is attached to a golf ball, it looks like. Okay. So right now my spring is in equilibrium. But if I take this ball and push it this way, compressing the spring, look what happens. I push the ball to the left. The force that's produced by the spring is going to be directed to the right, to the opposite direction. Well, if I started in this equilibrium position here, and I pulled it this way and stretched the spring by displacing the spring to the right, then the force produced by the spring is going to be to the left. So this tells us something kind of important about spring force is that it's always directed in the opposite direction from displacement. So here is our spring force equation, and this is what I'm going to ask you to memorize for the test. So the force produced by a spring is directly proportional to the displacement, but in the opposite direction. And then we have this multiplier here called K, which is the spring constant. So force is measured, and we'll talk more about that in a second. Spring force is, like all forces, is measured in newtons. Displacement is going to have to be measured in meters. And this is important because usually, it'd be really weird to actually displace a spring a meter. I suppose in some industrial applications, but in most situations, springs are going to be displaced centimeters or even millimeters. But in order to work with newtons and joules and meters per second, we've got to use meters for that. So in lab, you're going to convert whatever your measurement is into meters. One of the things that students sometimes trip up on. And then we've got this here. We call this little k, this lowercase k, is called the spring constant, and it is measured in newtons per meter. So how many newtons does it take to displace it a meter? So we're going to get to that in a second. But the main thing I want you to look at here is the force is always going to be in the opposite direction of the displacement. Let's just talk a little bit more about the spring constant. So the spring constant is basically, it's the amount of force it takes to displace the spring a given distance. So the bigger that value is, the more force it takes to displace it a given distance. We measured in newtons per meter. How many newtons of force does it take to displace a meter? Even though, like I said, you're never going to displace a spring a meter. We abbreviate with the lowercase k. Be careful, because remember, capital K is used for kinetic energy. And I know capital K and lowercase k don't look that different, so don't let yourself get confused. And it's worth noting that the bigger the value is for K, the stiffer the spring is. All right. And just so you know, values for K typically are in the hundreds of newtons per meters to thousands of newtons per meter in most of the springs we'll look at. Okay. Now, this is a graph that you should familiarize yourself with, because it will probably be represented on your AP test. They like to use this. This is called Hooke's law. Robert Hooke was a contemporary of Isaac Newton's. He studied springs, and he came up with his rule of springs, which has been called Hooke's law. Now, we don't really think of it as a law of nature. It's not that important, but it is a relationship that was determined long ago with springs, and it is kind of useful. So they often want you to look at this and determine spring constant. So the idea is this: if I take a spring and it's at equilibrium, it's got zero displacement, it will produce zero spring force. Now let's just say I then take it and I displace it 0.2 meters. I measure the amount of force on it. Well, it's making 1 Newton of force. I double this from 0.2 to 0.4. Well, look what happens. It doubles the amount of force. Now it's, instead of 1 meter, 1 Newton is 2 Newtons. If I double the force from 2 Newtons to 4 Newtons, the displacement doubles from 0.4 to 0.8. So it's a linear relationship. You double the displacement, you double the force, you double the force, you double the displacement. So therefore, if I want to find the spring constant, which is newtons per meter, that's this divided by this. That's just the slope. So you are expected to know on the AP test that if you have a force versus displacement graph for a spring, that the slope of that line is going to be the spring constant, because the spring constant is newtons divided by meters, right, which is what the slope would be. So to find the spring constant, I would simply say, let's just pick a point here along here. Let's go to 3 newtons, okay? 3 newtons divided by 0.6 meters gives me 5 newtons per meter. That would be my value for K, for the spring constant. And as I said before, 5 is a ridiculously small value. Usually we're talking in the hundreds or thousands, or certainly the tens. But anyway, that's how we would find it. So when I compress a spring, I do work, right? And that means that that energy is going to go somewhere. And the spring force, as we said in an earlier screencast, it's a conservative force, meaning it stores up potential energy. So let's just look at a scenario here. I have a spring that's at its equilibrium. It's unstretched or compressed. It's got 0 joules of energy stored in it, and I have a block that has no kinetic energy, so it's got 0 joules of kinetic. So my mechanical energy here, the sum of my kinetic and potential energy is 0. But I'm going to do work on the system. I'm going to apply a force across a distance, and I'm going to do 20 joules worth of work in doing so. Now, remember, work is energy added to or taken out of a system. In this case, I added it to the system, but this doesn't have any kinetic energy. After I finish pushing, it's not moving. So where is that mechanical energy? It is in the form of spring energy, US, spring potential energy. And since I did 20 joules worth of work, it now has 20 joules worth of spring potential energy. And if I let go of that block, what's going to happen? That spring is going to push it in the opposite direction. Since I compressed it to the left, it's going to push this object to the right. And when it gets to this position here, it has no more spring potential energy, but this is mechanical energy and it's conserved. So as long as there's no friction here to do negative work on the system, then this is going to have the 20 joules worth of kinetic energy. So basically, I put 20 joules worth of work into the system. I stored it as spring potential energy, and then I released it as kinetic energy. So you're going to see a lot of these type of conservation mechanical energy involving springs on your AP test. How much spring energy is in there? Well, uh, we're going to go back to that same diagram. This is the amount of force it takes to stretch or compress a spring. Here's the distance. Now remember that force divided by distance, so newtons per meter, this slope was my spring constant, but the area would be newtons times meters. Newtons times meters, that's force times distance. Hey, that's work. So I can look at this and say, if I take this here and I uh, apply enough force to displace it 2 meters, I see the amount of force was 2 newtons, but it's a slope one. So if I want to calculate the area under the line, that's going to be the amount of work done. So I get 2 times 2, that's 4, divided in half, that's 2. So when I displace it 2 meters, it took 2 joules of work, or in other words, I put 2 joules of spring potential energy into the spring. Now I'm going to double that. I'm going to double the displacement. I'm going to double the displacement from 2 meters to 4 meters. Well, what happens to the area under the line? Well, 4 times 4 is now 16. Take half of that, that's 8. I now have 8 joules of spring potential energy. So look what happened. I doubled the displacement, but in doing so, I quadrupled the amount of spring potential energy. And that tells me then that spring potential energy has this proportion to displacement. That the displacement is proportional to the square of the energy that it gets. Okay, so you get when you displace it distance x, you get a square amount of spring energy. So let's just try it again. I'm going to double it again. I'm going to double it from 4 to 8. So I have twice as much displacement. 8 times 8 is 64. Divided in 2, that's 32. Again, when I double the displacement, I quadrupled the amount of spring energy. So that leads us to another equation you've got to memorize, which is the equation for spring potential energy. And hey, this should look pretty familiar to you. We've seen this before. Spring potential energy is equal to 1/2 the spring constant times the square of the displacement. Now, it shouldn't be too hard to memorize. We've seen this before, right? We've seen delta x equals 1/2 at squared. We've seen for kinetic energy, K equals 1/2 mv squared. And now we have spring potential energy, US equals 1/2 K delta X squared. So yeah, it makes it a little bit easier to remember these things. These are our 3 big equations in physics, and they share some commonalities here. Let's see why it is that way, though. Okay, let's just dive in a little bit deeper here. Okay, so let's talk about the amount of work it takes to displace the spring. So work in this case, remember when we calculate the amount of work done, what we had to do is we said I take the amount of force times the distance, but I have to cut it in half, right? So if I displaced it 4 times 4 is 16, but I divide it in half, that's 8. So basically, the work is equal to 1/2 the force times the distance. So this work gives me my spring potential energy, and it's equal to this. Now let's talk about, well, what is this value here? what is the spring force? Well, we saw earlier that spring force is equal to negative k delta x. Now, for reasons I'll show in a second, I don't have to worry about the negative right now, but it's basically proportional to k delta x. So I'm simply going to take this here for spring force, and I'm going to substitute it in here because the work I was doing was against the spring force. So that gives me this. Now, when I just multiply this through, I get this equation. Now this was negative, so negative times this. So once I've squared it, that negative goes away. All right. So there's the equation for spring force. We need to put it up here. I expect you to have it memorized on this test. On future tests, I'll give it to you. But on our working energy test, you need to have access to it up here in your mental storage. So mechanical energy is conserved by springs, so therefore we use them a bit in the AP Physics test. So let's just look at this. I've got an object traveling to the left and it has 100 joules of kinetic energy. I have a spring that is at equilibrium, so it doesn't have any energy stored in it. So right now the mechanical energy of the system would be 0 plus 100 joules. But as this impacts that spring, it's going to compress the spring. Now remember, when I compress a spring to the left, it's going to generate a spring force to the right. And when the force is acting against the motion of an object, it does negative work. So therefore, the kinetic energy of the object is going to go down. So in this case, I'd say, well, it lost half of its kinetic energy. Instead of having 100 joules, it's got 50 joules. But the spring force is a conservative force, meaning that it can cause energy to be stored as potential energy. So what happens is, where did that 50 joules of kinetic energy go to? It ended up, that's missing from here, it ended up as spring potential energy. The mechanical energy of the system is still 100 joules. I have 50 joules of kinetic now instead of 100, but I have 50 joules of spring potential for a total of 100. Now, when this gets completely compressed, this kinetic energy goes to zero. It's not going to compress it anymore. It lost all of its 100 joules of initial kinetic energy. All of those 100 joules will now be present in spring potential energy, and then this will push it the opposite way. This will go to zero, and this will go to 100. Energy is conserved as long as there's no external work by a spring. So let's try this one here. Let's say I have a block of mass m is pushed against a spring of spring constant k, compressing at a distance x. When the mass is released, the block moves away at speed v, like we just saw in the previous examples. Well, how fast would it travel away if the spring was compressed a distance of 2x? Okay, let's just try to set up a proportionality here using what we know about mechanical energy and the different equations we have here. So we're going to start off by saying mechanical energy is going to be conserved unless we're told there's friction to do negative work on the system, and we weren't given that information. So we can say that the mechanical energy the system starts with should equal the mechanical energy the system ends with. Now, the mechanical energy it started with it had spring potential energy because I'd compressed it, but it was at rest, so it didn't have any kinetic energy. But afterwards, we can assume that the spring energy is going to go to zero and transfer it all into kinetic energy. So now let's just go ahead and say, basically what we're going to have is US is going to equal the US initial is going to equal the K final. So let's just substitute these with their equations. So I get 1/2 K delta X squared, which you're going to memorize, is equal to 1/2 MV squared, which you're also going to memorize. And that tells us that delta x is proportional, delta x squared is proportional to v squared. So therefore, delta x is proportional to v. So that tells me if I double this, I'm going to double that. So since delta x is directly proportional to v, that means that 2x is going to be proportional to 2v. But let's try this instead. So I have a block of max m, pushed against this is pushed against a spring of spring constant k, compressing a distance x. The mass is released. It moves away from the spring at speed v, just like before. But here's how I'm going to do this time. Instead, I'm going to double the mass of the object. So I'm sorry, no, I'm not going to double the mass. What if the spring had twice the spring constant? So the spring was twice as stiff. Now, your instinct might be, well, this is going to be double, but let's be careful with this, okay? Try the same thing again. So what we did here is, instead of doubling the compression, we doubled the value of the spring constant. Let's see what happens here. So we're going to skip that initial part. We know that the spring potential energy is all it has to start with, and at the end, all it will have is kinetic energy. Let's just cut to the chase here. This is going to equal this in a situation like this. So that tells us then that K is proportional to V squared, which means then that V is proportional to the square root of K. Now remember, the question is how fast would it travel? So for those who are still struggling with proportional reasoning, when you have a question like this, how fast would the mass travel, the velocity? You don't want any exponent on that. You want to just have V is proportional to something. And that something is going to be proportional to is the square root of K. So therefore, if I double K, that I put a 2 here to 2K, that's under this radical sign. So that tells me then is if I double K, the velocity is going to go up by the square root of 2. Last thing here. This is a kind of a cool graph that you'll probably see on your AP test. So let's just look at this. So I have a situation where I have a spring object system. So they're both part of the system. It starts off with 100 joules of mechanical energy. All of it is in the form of spring potential energy. So I have two things here. I'm going to have the kinetic energy shown in blue and the spring energy shown in red. So at first, the block has 100 joules of spring potential energy and 0 joules of kinetic energy. Now, as that object moves towards 0 displacement, what's going to happen here? So basically, when it is, think of it this way, when it is halfway compressed, so I went from 0 to 4, half of that is 2. Well, if I have half the compression, that means I have 1/4 the amount of energy still present in it. So I know it has to go from 100 to a quarter of that when I get to half the compression. Uh, and so basically, I'm going to get this pattern. So if I say 0.75% squared gives me this much, 0.5 squared gives me 0.25, 0.25 squared gives me this. So I'm going to get this pattern here as it drops down to 0 value. But what you've got to keep in mind when you're presented with this is that the kinetic energy has to always add up. So what they often do is they'll give you the spring and ask you to fill in the kinetic. And you just go, this is a conservative force system. So mechanical energy is conserved. If if when this is 3/4 of its compression, that means I'm going to have 56.25% of the spring energy still going to be present. So in this case, I had 100 joules, so I have 56.25 joules. This kinetic energy plus this has to add to 100. Unless external force is being done by, say, friction, that's going to be true. So when the spring force drops to 75, the kinetic energy must go up to 75 because 75 plus 25 equals 100. As the spring continues to decompress, and now it's only got 6.25 joules in it, which is basically, that would be 1/4 squared. Then the other energy, if I take 100 joules minus 6.25, I get 93.75. And then finally, when the spring gets to 0, I've got 100 joules. So expect to see a graph like this. The trick to this is they're usually going to give you either the kinetic or the spring. And you just have to remember the other value has to add up to 100 unless there is friction or some other kind of non-conservative force taking energy out of the system or adding energy into the system. Okay, so thanks for watching the screencast. It went a little bit longer than I meant.